Hi there! This series covers the first 100 Project Euler problems to help you learn how to solve unfamiliar problems. Project Euler presents complex math challenges to be solved with programs running in under a minute. Although they prohibit sharing solutions, the first 100 problems can be shared for instructional purposes. I encourage you to attempt each problem on your own before watching the corresponding video. I am currently learning Python and have been doing so since mid-January. I have no professional experience in the language and have only completed the Python for Programmers course on Execute Program. While I'm learning quickly, I don't claim any real expertise. Today, we're looking at the 65th Project Euler problem. As always, I will link to both the problem and my repo in the description. Let's dive in. Problem 65 is convergence of E. The square root of 2 can be written as an infinite continued fraction. The infinite continued fraction can be written in this periodic form, indicates that 2 repeats ad infinitum in a similar way. Square root of 23 is equal to 4 with the periodic repetition of 1318. It turns out that the sequence of partial values of continued fractions for square roots provide the best rational approximations. Let us consider the convergence for square root of 2. 1 plus 1 over 2 equals 3 over 2, and then going forward it's 7 over 5, 17 over 12, 41 over 29. Hence, the sequence of the first 10 convergents for square root of 2 are all of those. What is most surprising is that the important mathematical constant, E, the first 10 terms in the sequence of convergence for E are 2, 3, etc. The sum of digits in the numerator of the 10th convergent is 1 plus 4 plus 5 plus 7, which is equal to 17. Find the sum of digits in the numerator of the 100th convergent of the continued fraction for E. So, first let's look up Python E. That's a scientific. Okay, so we have a math.e. Okay. So we've actually done kind of both parts of this before. One is we've done the square root of 2 convergence as fractions. And the other is we have done finding the periodic form of continued fractions, so on and so forth. So, for this, there's a few different approaches that we could take. One is we could find the pattern here. The pattern here is a little bit more complex. Probably because it's E. Let's look up what this is. It is the base of the natural logarithm function. It is the limit of 1 plus 1 over n to the n as n tends to infinity. It is the sum of the infinite series, 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. Okay. So 2 plus 1 over 1 be... This would be a 2, 1. This would be a 1. This would be the same. So 1 plus 1/2 is 3/2. 1 over 3/2 would be 2 thirds. And 2 plus 2 thirds would be 8 thirds. And then how do we get to 11 fourths? Sort of, if we represent the 3 as a 3 over 1, it sort of looks like the addition of the previous two numbers. Not real addition, but like the addition of the numerator plus the denominator. So 3 plus 8 is 11, 1 plus 3 is 4. And then if we look here, 19 over 7 is 8 plus 11 is 19. 3 plus 4 is 7. And then it does not work anymore there. So I'm not 100%. I know that for the square root of 2, we were able to see this pattern where it kind of flipped and added. But it doesn't look like we're going to get something that easily here. Let's see. So we could come up with the first 100 and then do the convergence using recursion. But that doesn't really help us find the numerator very easily, I feel like. Um, yeah, okay, so I think if we find the sequence, the first 100 in this periodic sequence, let's see, the 100th conversion. So the first one is 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So the first one is 2, so we can kind of accept that as a given. And then we can kind of roll up our answers in a sense. So let's go look. File here. It is 100, right? Yep, 100th conversion. So we are probably going to want this precision. Um, without finding the sort of relationship here, the pattern with these things, I'm not quite certain how to go about doing this part, but um I think it'll be okay. We'll kind of worry about converting it back to a fraction at the end, I think. Okay, so we have limit in this case. We probably don't really need. Um, I'm also going to import math. E equals math dot e. Does that work? Looks like it's working. Let's go ahead and just print E real quick, just to make sure. Okay, looks okay. Um, I have a feeling this is going to end up being a dead end because of the lack of precision here. But we'll find out. Okay, so there we were getting the square root of this. Going back to what our E actually is. Um, there's going to end up having to be a better way of converting E. Because we need a lot more precision than this provides. Um, okay, so this is E to 30 decimal places. We probably want even more than that, actually. Let's say 1,000. Okay, so this is basically just doing the infinite series until we get a particular precision. Um, okay, so thinking about this back here. Okay, so in order to find the conversion for the this, for like the square root of 23 or 2 or whatever, what we did is we got the square root in a way in using decimal. And we had a precision of 1,000. So if we do something similar to that, we will probably be okay. Um, so let's see. We could do computing, these factorials. Kind of like they've done here. Actually, this is actually most of our answer, because this here, the counter and the denominator, might actually be a good approximation of E. Maybe not, though. Okay. So I think we probably want to do something like this, where we find E to the nth digit, or to an arbitrarily large place. I don't want to just take this code. I mean, let's be real, I actually do. But let's make sure we understand it. Delete this part. Delete this. And here, instead of just decimal dot decimal, we want to do context dot divide. I believe. Yeah. So if we do this, we will calculate E, and this specifically is E up to a particular N, which we will give it. So first we're going to do E equals compute E and pass in 1000. And then, now that we have E, we are going to go through and find the period of it. Okay, so create our little array. A of 0 is... we don't actually want root here, we just want E. And we don't need this anymore. And then that's just... and then here I am just going to say wall period, length of period rather, is less than 100. So when we hit 100, we don't care about that part. So we're just calculating the continued fraction. And then once we have that period, we can go ahead and add up our convergents. So actually 99. Let's see. We want to kind of start on the bottom. So 1 over whatever the very last part of period is. And then working backwards to add... okay, so say the first digits we're working with are 3, 2, 1. We're going to start with 1 over 1, which is just 1. And then we're going to add 2, so 3. And then it'll be 1 over 3. And then we'll add 3. And then it'll be 1 over that, and so on. And convergent is equal to 2. Or actually, I'm just going to start convergent is equal to 0. And then for I in range, if the period -1 to -1, stepping down. then what we want to do is, at the end of this improvement, print out that. We definitely want to add the 2 on there at the very end. Okay. So it'll be 1 over period I, which I am going to just call P. So actually, let's just do and we want to do effectively convergent plus equals P. Or we could start it out with the very last, even though we know that's wrong. And then actually, I think this is just... I'm going to duplicate this line. And obviously I can just do this. And I don't need that or that. Yeah, and I think that'll give us the correct answer. Let's see if it works. Okay. So we're looking pretty close to correct here. Now, how do we represent it as a fraction? Oh. We want to do something like that, I think. So let's see. Everything inside of period is an integer. If we keep doing this, divide by 1. Let's do this differently. I'm just going to call it then for denominator and num for numerator. And we start out with this. So 1 over whatever this last convergent value is. And then every time we come to a new number, we add that number to the numerator and denominator. So now add val is equal to whatever the period value is times whatever the denominator value is. So 1 over 2 is also represented as 5 over 2. So that is obtained by 2 times 2. So period times the denominator. And then the numerator plus equals the add val. And the denominator would stay the same, but it needs flipped again. Changing this to 100. So we add 2 at the end. Yeah, I think if for every single one, I do this and then I flip the numerator and denominator, that'll work. Let's find out. Actually, I could just say temp is equal to num plus add val, and then is equal is equal to den, and den is equal to temp. It's going to be hard to tell whether this works. Let's bump it down to 10 just to see. I want to see it work. Okay, so if this works the way I think it does, we should get out the 1457 over 536. No, not even remotely. Okay, so something is wrong. So 1 over 1. Ooh, it's going to be hard to tell. Let's bump this down to 3. And that should give us 8/3. But it doesn't. It gives us 11/4, which is the fourth one. So we have an off by 1 somewhere. Let's try that. Okay. Change that to 10. See if we get the correct answer of 1457 over 536. Okay, so now I'm confident that this works, and we can go ahead and bump this up to 100. Those are very large numbers. Under the conversion of the continued fraction-free sum of digits in the numerator. Not sure what went on right there. Sum of num equals sum of D for D in string. Okay, so that's kind of a lot for squeezing into one line like that, but basically I'm converting the numerator to a string, and then for every item in that, and then I'm creating an array out of that string, so each character in the string becomes its own string in an array in a list. And then for each item in that list, I convert it back to an integer, and then I sum up the list with the integers. Let's see if that gives us the correct answer. 4434. Fingers crossed. No, not the correct answer. So, what did we do wrong? Other than forget to add the 0 back here. Let's see. This is the same problem we're looking at. This doesn't appear quite right. Continued fraction free. Okay, I feel like this is not getting us on course. Let's go back to 10 and print all of them out. Just to make sure we're doing things right to begin with. Although that doesn't actually confirm we're doing things correctly. Because it's not the same. It's not the same. We're doing things kind of backwards. Let's see if this is correct. Like, maybe we gave it... Maybe we have an off by 1 error? No. Do we have an off by 1 error the other direction? This is kind of a stab in the dark. I kind of don't think this is the real issue. Okay. Doesn't seem like it. I wonder if upping the precision will change the answer. Just gonna comment that line out again. And maybe this one also. Interesting. So we're going to do this. Can I just import sys? And we'll set it at 10,000. Okay, so definitely a different answer. And a much larger answer. So let's see how close we are with that. Nope, still not. I think we're getting... That is, like, pretty similar to E. We'll just print out E real quick. Okay. So our convergent is pretty close. We're just not being precise somewhere along the line. I'm losing precision somewhere. Probably here. Well, no, that shouldn't matter because those are integers. Oh, goodness. Okay. Taking a little bit longer with that now. Still only a few seconds. I'm going to make this be context dot divide so I can kind of see where I'm going. Since it's arbitrarily chopping it off somewhere. Oops. My bad. Yikes. Uh, just do that real quick. I believe this 450178 is a number we have not before encountered. Or at least not put into our little answer check. So let's see if we're correct here. It's not. So I think there's something I'm missing here. Something that, like, maybe should be obvious. Especially since, like, the first 10 appear to be getting the correct answer. Let's see if we can find the first convergent. Okay, so that's doing 2 plus 1 over 2, which is what I told it to do, but it's wrong. Let's see if this gets 3. We did already try 3. Found that we got the correct answer. Fourth conversion, 2.75. Is that 8/3? I believe it is 8/3, but no, it's 11/4. That's right, we skipped the third one. Let's do limit of 11. One, two, three, 4, 5, 6, 7, 8, 9. They don't tell us what the 10th is. Okay, so if we do this kind of manually, let's go ahead and bump this limit up to 20. And double check our... Okay, so it's 1 over. It's always 1 over. What's curious to me is how to find where I am wrong. And I think I know. I think it has to do with the fact that I'm finding the wrong number in the period somewhere. So let's... in here... Let's see. So I want to compare this list to the list that I have over here. We'll just comment those two lines out for a second. And all of that. Okay. So I feel like there's an obvious issue here. This doesn't seem right. This should not be this big of a number. Let's see where we messed up. Okay, so I see a 120, a 1288 here, which is not here. But 212, 11, 4, 11, 6, 11, 8, 11, 10, 11, 12, 11, 14, 11. This is a pattern. 20. So this should have been 22, and it comes out as 6. So something went wrong. And actually, let's see. So we know it starts with 2, 1, and then it's 2, 1, 1, and then it's that 1. Okay, so now that we know that, instead of computing E and finding the period, the other way, let's go ahead and throw away a bunch of this code. And hopefully I don't need to be doing that anymore, but I'm going to leave it just in case. And this calculate continued fraction period. This is going to become limit minus 2. Delete those two lines. While length of period is less than limit. And we want to start here. We want to have the 2 and the 1. And what is good thing to call this? I'm just gonna call it rem for remainder. Not really quite a fair way to do it. And 1, 1, and then rem times equals 2. So basically what I'm saying is, hey, I found this pattern when I actually went and I looked at this thing. Oh, it's not multiplying by 2, it's adding 2. Much more better. And I bet you we can add these back in here. And get that real correct answer. I'm not going to be able to print out the thing I don't have. Okay. Now that we're not getting an absolutely bonkers number, and it looks like we're converging on the correct solution, let's see if 272 is the correct answer here. And of course I have to make sure that it knows I'm not a bot. I'm much more confident in this answer. Yes, okay. So, here, there was probably a better approach, I feel like. But basically what I ended up doing is I looked up this period. I noticed this pattern of adding 2 and then 2 1s. Which wasn't necessarily noticeable in this part. And then I went ahead and I even used context before this point, and I don't think I need this anymore. So I said, okay, we start with 2, and then we have 1, and then we have 2, 1, 1, and then it's 4, 1, 1. So we created this little, just figuring out what the numbers in the period are. And as far as I can tell, that it seems to be infinite. And then we go, okay, so for every single one of these, starting with the 100th, we want to divide 1 by that number, then add the previous number, take that answer, divide it by 1, add the previous number, divide by 1, add the previous number, divide by 1. And this little motion is the turning over a fraction. Because when you divide 1 by a fraction, the result is just the turned over fraction. And that's what I'm doing here. Okay. So, probably not the absolute best way to do this because we did kind of take this period and cheat, but this, I think, is the real meat of solving the problem. Calculating the continued fraction period was not working out for me, and I'm not 100% certain why. Probably a precision error. But again, that's the correct answer. It found it programmatically. Yeah, I think I'm going to call it there for today. I'll catch you in the next one.